Python developer. I majorly focus on machine learning, and I also do a bit of backend development. And I write. I enjoy writing because it's an interesting way to, validate thoughts and share them with other people. Um, I also have some experience with, teaching in settings like this, and majorly to students. So it's nice to also do that here. AI facilitators. Um, my major research interests are in process control and in energy systems. So applying machine learning into process control systems and energy systems. It's a little bit unconventional, but it's because I have a background in chemical engineering. So I'm interested in applying machine learning in that domain. But with the usual machine learning areas, I'm interested in NLP. I've done work in NLP, in both audio processing and text as language processing. I've also done research in vision, to computer vision, dealing with microscopy images and regular images that you interact with on the internet. So I played around with stuff, and I'm interested today in sharing with you more on free text and NLP, following the session you had in the morning a bit. We're all so I hope you all enjoy the session. It should be fun, and we have some interactive bits too, so stay tuned. I hope everyone saw the collab notebook on Discord. I want you to, if you've not already, I want you to open it, create a copy, so you can also run the code as I do. And if there are any errors, you can just put it in the chat. I would try to monitor the chat as much as possible, and then we can have a fun time. So let me share my screen. You should see my notebook in a bit. Okay. Can we see my screen? Maximize this. Can we see my screen?
Yeah.
Okay.
Yes.
Thank you very much. So, for those who have taken a peek, the lab is on free text and natural language processing, and we'll be using the Nigerian Constitution as a data set. I just thought it was interesting to explore a document that perhaps we all should know, but most of us don't, because who wants to read the Constitution, right? But yeah, it's an interesting document. Teju, were you saying something?
Yes, can you please zoom in a bit more, just a little bit more? And also, maybe we can close the side panel for now if you're not using it. And I was recommending to have this theme in white. Maybe we can change it to white instead of that color, by your preference.
How is it?
Looks good, I think.
Is it better?
Yeah, I would say.
To change it implicitly from these settings.
No, I think it's, if you're looking for the theme, if you scroll up, like default dark, you can change it to white. The first one. No, yeah, the theme, yeah, dark theme, that you actually were in the right place. The site, if you go to site. Yeah.
I think I'll just zoom in.
Yeah, I think zoom in works as well. Would you like to use a dark? Do you want to keep the dark theme, or you want to change it to a light theme?
Very dark theme, unless the lighting is preferable to other people.
Okay, then that sounds good.
Very much. Thank you. So if at any point you feel I still need to enlarge the screen, it's fine. I can figure it out. But let's see. So yes, the Nigerian Constitution is what I was talking about. One of the, like you've learned today, models do not do well with raw data. So you can't just take in text directly and automatically use it to make inference. They need to process it somehow. Right? And today we've learned about many ways to do that, but in this lab we'll be diving into that in more detail. But I thought it'd be interesting to do this from ground up, so by scraping some data, since you guys have already done a bit of work on scraping. So yeah, we have beautiful soup imported. So we import beautiful soup, we import the request model, and we import the regular expressions, right? Our goal is simply to scrape the entire content of the Constitution. It might be interesting to take a look at what the Constitution is. So let's take a quick look at the Constitution. Right, so as you can see, it's just a single page, right? Everything we need to get is just on this page. So scroll down, you see the deep dive into more details on the Constitution, which makes it easier for us, meaning we just have to scrape a single page and we're good to go, right? So let's return to our screen. So okay, so I think increasing the font size works for the code cells, not the editors, not the markdown cells. That was what happened. But the code cells are larger. So what we do first is we use Beautiful Soup library to get the content of the website, right? After we make a GET request, it just gets the HTML essentially from the website. And then we use the LXML parser to parse the content of the response that we get. And when we do this, we have one final step. We decide to replace white spaces with a single space, because it makes it easy on the eyes. And I'll show you why. So we can see if we took root.text, yeah, and just to see the way it is, right? You notice that there is a lot of \n/n. This is just new line, and then there are a lot of other characters that are typically white space characters. You don't want to see them, right, in this way when you're analyzing the text, but because they don't help the visual look of what you're trying to do, right? So in this particular line, we are using regular expression to substitute all white spaces that are duplicated and replace them with just a single white space. That's what's happening. So substitute one or more white spaces with a single white space, and that gives us text that looks significantly easier on the eyes, let's just say. So you see, this is what we have here. You can run this on your end, you get the same result. So yeah, then in the lecture today, you also learned about tokenization, and you in different natural language tasks may have to do with text, where each data point is perhaps a paragraph. Some cases it could be sentences, some cases words, right? But data usually comes in like a corpus, like we have here. We just have all the text in the Constitution, right? There's not much in this form, right? There's not much definition of order. While we could have scripts in such a way that there's some more order, right? It's interesting to see how we can go from a relatively disordered state like this to something that is more useful to us. So yes, the first thing we discussed is sentence tokenization. We thought a bit on this in the lecture too, but the idea is when we take a look at this constitution words, right, the output, we see it's just everything together, right? But how do we separate this into sentences, right? One way people think about it is split the entire string by, you know, the full stop, that's the period sign, because I mean period sign is usually signifies the end of a sentence. I mean, it's an interesting way to look at it, but if you look a little bit closely, you see you have cases where we have one, right, one, and then you have the period sign. In this case, it does not signify the end of the sentence, right? But it's a period sign, so you would take out that as a single sentence, and then it will have submit your constitution as another sentence. That's not what we want, right? So if you tried it, you could say just use the split function and define the parameter. See that we have the text split up. Looks nice, but there are some parameters. So we see the ones where we have just numbers showing, right? So it gives us more of a limitation in that sense, right? So, but in a more literal sense, what could represent the presence of a new sentence? Yeah, could be the new line. So the new line character. So the new line character in in Python and programming generally is this \n you see, right? So if you go back to look at the root text, see \n here, and then you realize that if we decide to split by \n, we might get a good representation of sentences from the constitution, because a new line means, in most cases, a new sentence, depending on how the document is structured. So let's try that out. And that's what we do here. So first, this is a list comprehension. What we're doing here is we loop through every line in roots of text, as this text up here, and then we split, right, by \n. Now, you will notice that we have a number of \n values that just come together, which we tried to remove earlier in the beginning by substituting all the recurring white spaces with a single space, right? But in this case, since we're going back to roots of text, we will still encounter this, recurring \n and recurring spaces, white spaces across the text, meaning we'll have some text that will be essentially empty, right? Now, when you have text, so let's say we have a sample, and if you try to so if we split this, we have some empty strings because there are cases where \n occurs at the start, and then there's no characters between them, so it's still an empty space, right? Because that's what the split function is trying to do. Meaning we have to get rid of this particular samples, right? And the way to do that is to use your if condition. For those that are more familiar with Python, this would be somewhat direct. So we can say that for let's say for I in this split, right, only take a value of I if that value is, or if that value results to like a positive Boolean, and then you see that now it strips out all the empty string. Because when you do if I for an empty string, right? An empty string, when you evaluate it using the Boolean function, is negative, simply negative, right? If there was something there, then it would not be negative. So that's the logic we use here. We use that to look through the lines and then only take out the lines that are relevant to us. We also strip the lines. So something that is interesting is the fact that, you know, when you have a line, let's say you have a string like this, just cooking, right? You can strip out the white spaces at the start and at the end using the string.strip function. So when we do this, it's out just cooking, and then we're good to go. And it's relevant in this case because there are cases where there are white spaces at the start and at the end of the text. So we want to get rid of that. For instance, you know, at the very beginning, you notice that Constitution of the Federal Republic of Nigeria starts with a number of white spaces. All right. In this case, they are new lines. And even when we replace them, there will still be an empty white space. So we need to remove all of those white spaces. To do that, we use the strip function in every case where that happens. Right, we do that and we're good to go. Right. So first, before I continue, does everyone follow the whole idea behind looping through all the texts and then, you know, taking out just the lines that are valid lines, right? And then also stripping the lines to ensure that there are no spaces. Because, you know, if you have a line like this, just a way to make it clearer. If you have something like this as a line, right, and you evaluate the Boolean value, this is true, but then it's empty. So what are we doing, right? But then if you strip this line, then it's no longer true because you've removed all the white spaces, in which case you now reveal that it's an empty string. So it's quite important. Let me see if we're following. So I need responses. Are we following? Do we get the idea behind what we're doing here? Somewhat foundational. And if we don't, you know, we can always discuss it. Okay. Thank you, Olatunde. Okay. Good. So something we're also doing, you know, I've just discussed this part. Typically, one will just have, you know, maybe line.strip here. Then we say we're done with that based on everything I've explained so far, right? But we still want to remove any other characters that might be or any white spaces essentially that would be in the text, right? So something we also do is we retain the regular expression command we had before. Remember that, you know, while we're scripting, we use this regular expression to just script out everything but from the entire text, right? And now that we're interacting with the text line by line, we still have to do the same thing. You get so while in this case we replace, you know, all the white spaces with a single white space, right? But, you know, we still have to also strip the line, right, to ensure that we only take out what is relevant lines. In fact, we could also look at this as, let's say we take this and then we change the order of what we're doing. It still works. So we replace all the duplicate white spaces with a single white space, and then we strip to ensure that there's no white space at the start and at the end. Note that it does not affect the white spaces in the middle. right? So an important distinction, right? There's still a space between the and boy. It just removes from the beginning and from the end. So when we do this, we get something that looks more like, lines, but then we still see, phrases and then numbers, right? And we don't particularly want those things just like that. We want things that are better, representation of sentences, right? And in that case, it means we have to do more, right? We have to do more cleaning of the text. So what we do also is, if you remember in your lecture today, someone asked a question about how you handle uppercase and lowercase, right? But what last said was, in most cases we just make everything lowercase from an earlier point so that we don't deal with capital R in right being different from smaller case or lowercase r in right. So we do line the lower first to just take out the cases and make everything uniform, and then we use regular expressions again to replace all the digits with an empty string. So we remove all digits from the strings, because in the Constitution most of the digits are not representing any numerical value. They're just like the counts, like the index of the different sections of the Constitution. So maybe they are listing a number of things, right? So in this case, you see it here, they are listing some of the rights. So you don't want the numbers, they don't communicate much to you. And in this particular lab, we're not bothered with them. So we remove them from the text, or we also make the text lowercase. And the final thing we do to filter is we limit the validity of a sentence to, to lines that have more than 6 space separated words, right? Or space separated strings. So we split the line and then we check to see whether it has more than 6 space separated strings. So because that helps us have a defined, representation of a sentence. Now, we could change this 6, we could reduce it, increase it. That is actually our choice. You get. So for instance, I might say, oh, some words can be valid if they are more than 3. All right, so I could say, okay, let's leave it as 3 instead of taking it as 6. So my choice is how I decide to define the sentence in this case. So I'm at will, all right. So I can do that, and I still get the result I want to get. So it seems here that we have strings that look more like sentences, at least across the entire Constitution, though they are not exactly they might not follow the exact sentence format. So the question is now, what about other forms of tokenizations, right? What else can we do to this text to make it, tokenized? Because we only considered it on the sentence level. One thing to consider is word level tokenization, right? So when we're tokenizing on the word level, something we want to do is we want to split the sentence, right? And the assumption is that every word in a sentence is separated by a space. So if, for instance, you have a word like I'm looking for a word that would have like a hyphen between them, a compound word. So let's just say, for instance, we decide to something that could be in the Constitution. We decide to have the word like this. Let's say this is how it's represented in the Constitution, right? This will be taken as a word because we're splitting by space, not by this hyphen. So we just split that like that, and then we call that our word tokenized lines, and then we visualize, we display a portion of it. So you see here that we have it separated into words now, which looks good, to be fair. But then there's also the concern that, what happens to punctuations? So if you look at this example in particular, power as to matters of evidence, right? As at evidence, you see that, the full stop is with evidence. Now, in some cases, you might want to tokenize your data set like that, right? But if you don't have a lot of data, you might, this essentially means that evidence with a full stop is different from just evidence on its own as a string, right? Which might not be what you want. You get. So the question is now, how do you treat even the punctuations as individual tokens? To do that, we use the Natural Language Toolkit, NLTK. It is pre-installed in Colab, so you don't have to install it on your end as you're running this. But if you wanted to, you would just do a pip install NLTK, right? Is that direct? So in this case, we install it, we import the word tokenize function, because that we're trying to do a word tokenization, right? And then we download the punctuations model from NLTK. So let's test it. So we see that now, even the comma, right, is taken as a token on its own. We see the exclamation mark. We also see the exclamation mark. Something that's interesting is you see that it takes the apostrophe S as a single token, right? Because contextually, you don't want to split house into how, then just the apostrophe and then just the S, right? You want to retain the context that, oh, this was like an abbreviation for how is, right? So that's an interesting thing to note. So we now decide to do that instead to our data, right? And then we word tokenize constitution lines. Okay. So now we've done this, but does it look good? Let's see. So we look back to the sample we looked at before. Power as to matters of evidence. Now, evidence is separated from the full stop, right? So we see that, okay, this better communicates the fact that, okay, whilst this marks the end of the sentence, evidence can be taken as an individual token as well as the period sign. Another interesting thing is character level tokenization. In this case, let's say we want to tokenize based down to individual characters, right? An interesting way to do this is to just directly use the list constructor in Python. So an interesting thing is when you call this on the sentence, right, it splits it into individual characters. So when I run this, I don't need the print function here. When I run this, you see the way it splits this. Let me print it so it's easier for you to see. So the idea is it splits it into individual characters. So you see everything is based on the character level. Now, the question I have for you guys is why? Why do you think when you call lists on the sentence, which is a string with characters, why does that automatically split it into a list of characters? What property of the sentence makes that happen? So I'm looking at the chat, so you cannot mute. Anybody have any idea? Any ideas? Any ideas? Any ideas? Okay. An interesting. Okay. My question was, when you call the lists constructor on a sentence, why does it split up the sentence into a list of characters? Like, why does this work? Did you get that, Josiah? So do you have an idea?
Oh, I can unmute. So I think it's the follow. If I'm not mistaken. Does that answer the question?
What do you think is the follow?
Yeah. So the
Okay.
follow goes over each characters in this sentence.
So I mean, that interests me to place it. Others have also dropped some things in the chat. Usman said sentence was stored as a string which can iterate over. So yeah, similar to the idea you're trying to pass on with the for loops. When you have an iterable, which a string is an iterable, right? You can pass it to the list constructor, because if I hover over the list constructor, you will see that it takes in an iterable. That's what's specified here. And then once you do that, then you can create a list out of it. That's interesting to note. Something else that you might be interested in learning about is subword tokenization. Now, for some languages, it's useful to break down words into smaller units, right? And it's useful when you have like compound words that have different components, and you want to break it into smaller pieces. This helps us in cases where we don't have a lot of data. So you don't have a lot of data, but you want to be able to use your tokenization on even words that are not in your data set, right? So a way to do this is to split the text, right? That's the word into even smaller words, because it makes it easier for you to recognize. So in new words, right, you probably pick up some parts of the word that's already exists in your subword tokenization. For instance, if you had irregardless in your actual data sets, right, and then you have a new word that is fearless, right? Even though fearless was not your original data sets, your tokenizer can recognize the less already from its own subwords. And then if, for instance, it has fear already in the data set, then it's just split into fear and less. If it does not have fear, you have it split into FEAR or something like that, or F and then ear. So it would do interesting things like that, depending on how much information it has already about the word fear. So to do this, you can use the library sentence base. So we'll be installing I'll be importing libraries like this throughout this lab, just so that you can experiment using libraries instead of doing everything from scratch, because it might help to understand how things are done in practice. So something we do here is we write our data, all these constitutional lines, into a text file so that we can use it to train a sentence base, right? A sentence based model, essentially. So this sentence base, we pass the data directly. So if I open my side panel, you see data, the text, this guy. You could even open it really, and see what's inside. Let's see this loading. So you see that it has the lines in the Constitution as we have in our variable. So yeah, we do this and we train. When we do that, we also declare a vocabulary size. This is just a way to limit it. We could make it larger, but there are inbuilt limitations in the sentence space trainer that limits how large the vocabulary can be, right? So we just pick 2000, or you can experiment with this. You can change it to some 100 to 200, right? And then see how it works. But in this case, when we do this and we load the model file, because we declared that the model prefix should be M, so it saves it as M model, right? So you see it here in my file menu. So when we load this, we can now see, okay, so what happens when the word is known, like the word constitution, which appears, as you'd guess, a number of times in the constitution, it takes it as a full word on its own, because what the tokenizer tries to do in this case is it's based on the frequency of the word. So the more frequent a word is, right, the likely it is that the word is taken in its entirety as a full word. Right? But the less frequent it is, the more likely it is that it splits the word into bits. That's the working principle in quotes behind the BP tokenization that we're using here. So it makes it easy to handle words that are rare or words that are not in the vocabulary, right? By decomposing them into units. So as you see here with the restitution rather, it splits it into rests first, interesting. Then I, then TU, and then TIUN, again, which you must have gotten from other words in the vocabulary. So it's an interesting way to also pass across the idea. And we can also run this on like an entire sentence, right, to include everything. So we see subordinate jurisdiction. When it gets to high, it cannot take it again. It cannot take it as a full word anymore. Perhaps because I've excluded it from the vocabulary. And so you're just taking it as individual characters, right? And then same with cohorts. So interesting way to tokenize it. It helps, particularly like I said before, with low resource languages, and when you're dealing with limited data sets. So any questions so far? Do we get the idea behind tokenization as a whole, and even if it's particularly this subboard tokenization? Any questions? Any questions? Any questions? I'll hold on for 10 seconds before I continue. So Kelvin is asking if we can go over subboard tokenization. Sure. So the idea is that you have words, right? Words as a full unit, and you're trying to tokenize them, but you are now looking at words not just as a full unit, but into its components, right? So the idea is what components are in a word, right? How can you split a word into different components, right? And then still get some meaning from it. That's the fundamental idea. So to do that, all right, what we do is, one way we do this is using byte pair encoding, all right? And what it tries to do is, so giving you a data set of constitution words, right? So we have all these words in our constitution. It looks at these words, right? And it also looks at their frequency. So the more frequent a word is, the more, assurance the tokenizer has that it can be taken as a whole. So in case of for that word, it will be like a word tokenization. But for words that are not too frequent, right, it prefers to split them into smaller bits. So let's say this authorization word was not like a recurring word, right? You might want to split it into author is maybe A and then TION, you get. So splitting words into bits to make it easier for a model or a language model trained on this to understand a new word that might have a component here, right? Maybe there's another word, maybe we have to now use the word authority, right? Right. So in that case, I might say authority, right? So splitting the word into bits that you might have been familiar with earlier. That's the idea behind byte pair or subword tokenization. So it's quite literal. So subword essentially meaning that we are going below the level of the actual word that you get. We are not going fully down into character tokenization, right? We're just going a little bit, down the level of from word down to subwords. So that's really the idea. Instead of taking the words as a whole, why not split them into bits? And you see that with the restitution here, right? And then the subordinate revision. Understanding how the algorithm itself works is not primarily a concern right now. So you can check it out later, right? But is the context of you can take the word into bits and then use that later going through words that you're not too familiar with. Do you get that? Okay. So we can quickly take a look at a visualization. So you learned about data visualization some weeks ago. But the question is when it comes to text, how do we visualize, right? What sort of visualization method do we use? So something we can do is first character level visualization. I want to ask why character level? Does that work? Right. The idea is let's find out. So since you can do character tokenization, let's try a character level visualization. So when we do that, I just regenerate this. You see that, okay, it just tells us how frequent different characters are in our data sets. Is no surprise that the space, that's the white space, is most occurring, right? And then we have E, and then we have O. But this does not tell us much about the words in data sets. So while it's nice, like based on just telling us what the characters are, like their frequency, we might want something more, right? So let's try out word level histograms. So with word level histograms, what we're doing is we're just splitting the constitution into different words, right? So then we use the numpy.unique method to essentially count, right? So I will show you what is inside word frequency. It's similar to what we did up for the character level histogram. So it splits the data into words, right? And then you see that we still have some funny things in our word histogram, but it splits into words and then it tries to count them also. So how many times does this appear, right? When we do that, we're able to get a frequency representation of the words in our data set. Okay, something I tried to do here was to see what word appeared the most, right? So the second array here represents the frequency count. So the idea is if we take the argmax of the second array, right? And the argmax is just the index, and we find the word in the first array that has that index. That's 4248. That's what we're doing here, right? Because the first array is just the array of all the words. So when we find the word at that index, tells us that, okay, the is the word that appears the most in, the Constitution. Not too shocking, really, but, it's interesting. So yeah, we move. So in this case now, I'm only visualizing a portion of the words because they are too much, really. If we take the we can check out how many words there are at this point. So we can, okay, going to do this. Get shape. So there are 4,660 words, right? We cannot possibly visualize all of them, which is a limitation of visualizing like this on the word level, because we cannot see everything. If we try to do that, all right, it would just model everything up. So we can try it. Here we can see that, okay, conduct appears the most amongst all of this. But then what if we decide to say, let's look at everything, visualize the whole thing, what happens? Take a while, but it brings up a plot that is somewhat snapping, meaning we cannot do much with it really, because we are limited by the size of the visualization. We have to make it very large for us to even see the different bars individually. So yeah, like I said before, it takes a while, but not too long. In this case, we can see this one clearly because we increase the figure size to like 10 by 15. Yeah, we can do that. Now what I did up here. So what frequency dot shape gives us the shape of the words, right? The word frequency on its own is a tuple, right? So it's not you can check the type. Word frequency is a tuple, not an array, but it's when you access the elements of the tuple that you now get the arrays. I can check, their shape and things like that. So you can do the same for both 0 and 1, right? So the numpy the unique returns a tuple, but a tuple that contains 2 arrays. That's the idea. Some of this, okay. Was that the question you wanted to ask, or did you have another question?
Yeah, that's what I wanted to ask, and you have answered it.
So you see, this is what we get when we try to visualize everything directly. I mean, we could probably increase the figure size, but you'll probably span the length of this whole note before you can even see, the different words individually, right? Which is why we limited it to 20 before. So you see that this does not work too well. But then we can talk about the word cloud. The word cloud was briefly discussed in, I think, after a question in your lecture. And what it does really is it tries to represent the frequency by font size, right? So larger words essentially means that they occur more. So you see house, you see state, you see office person, right? I set the maximum words to 6,000 because the data sets has less than that. So that we still capture all the words in the data sets, right? And what we just do here is we pass all the words in the in our data sets. Remember that while we're doing the word level histogram, we collated all the sentences back into a single string here. So we just pass that string to the, and look at the string a little bit here. So we just pass that string back to the word cloud, and then we generate what we see here.
Okay, please, can I ask a question, please?
Yes.
Okay, is there anyhow you can actually tweak this code, the word cloud code, to get the word cloud image on a round form? Is there anyhow that can be done?
You get the word cloud image of what? Sorry.
On a round shape, like round in shape, like adding some form of design. Is there any how
Not
that can be done?
with that. So
Huh?
I mean, you can maybe if you check the documentation, you might see something interesting about that. But most of my experimentation with the word cloud has been, rectangular like this. But
Okay.
it's possible that there are libraries that will allow you to, create a word cloud in like a circular form. That would be interesting to see.
Okay.
Okay. So yeah. So the question also is, from your own, from seeing all three plots, which do you prefer? All right, so you can just drop a message in the chat, and you can tell me why also, why you prefer it. Because we've had histograms, interesting looking histograms, but which you prefer and why, if your goal was to understand the frequency of the words in the data sets. So let's just drop some messages in the chat. Okay, so it looks like we prepared the word clouds, and I think I agree because, it's can we have the I think that's it.
Yeah, I can hear you. You were not talking for a while. Too.
How about now?
Yeah, sure, but you're echoing.
Okay. Thanks.
It's better now. I
Yes.
think it's better.
Okay. So we all prepare the word cloud because it just looks better, really. But also it's important to note that while the word cloud tells us more information, it gives us information about the frequency, right? We are still going to have, trouble with understanding words and their relationships. It just lets us know how, how the words interact in the how the words, are present in the data set really, but not much about how they, relate to each other or anything like that. But I mean, the word cloud is visually appealing, like we've agreed on. So there's always that. Okay. I want to dive into vectorization, but so far, any questions? Any questions so far? Okay, since there are no questions so far, what I'll do now is I'll introduce the idea of vectorization as it's from the lab point of view, and then we'll pause for a while because I need to switch devices so that we can continue the class without an interruption. So maybe we take that as a break. It's almost an hour. Okay, so like I've said, we've been interacting with the text in in the string format, and it's been interesting. But the models that we'll be building later on, and computers themselves understand numbers better. All right, because when you think about it deeply, even the strings are stored implicitly under the hood as numbers, sequence of numbers. So the question is, how can we now transform the text we have into a form that the systems we are building can understand? Right. One way is the bag of words approach. Right, and this method really tries to represent text data in a form where you either focus based on you use either the frequency of the word or the presence of the word, right? And we're going to dive into both. So using the frequency of the word to represent the word, or using the presence of the word to represent the word, right? And of course, the order of the word will be lost, like you learned in the lecture today. All right, the structure of the word will not be retained when you just put things into a bag like that. Because think about it like a literal bag. When you just put things into a bag, and we're assuming that the bag does not have compartments, so you just put all the words into the bag. There is no arrangement in the bag, right? So everything just jumbled up, but they're all in the bag. That's the idea, right? So that's the concept behind the bag of words, and I guess the reason why it was named bag of words. So we'll cover one-hot encoding and the TF-IDF shortly, but for now, let's take a break so you can get up and stretch. I think we just passed the 1 hour mark. So let's just take a quick break and then we'll continue shortly. Also, if you have any questions, you can always drop them in the chats too. And then I'll just address them once we resume.
Yes, there are. Fortunately, I'm very short break is currently switching device. That's why you cannot hear anything. Do you have any question so far?
Hi, Cedric. Hi, Cedric. Can you make me co-host on this account?
Hello, Fortune. It is echoing. It's echoing. You are echoing.
Still echoing now.
Yeah, I think it's better. It's better now.
I already muted your other accounts. Okay. Thank you, Cedric. Okay. Here we need to reload some cells, but we can always just discuss. So we're about to get into vectorization. So I'm going to run all cells before this. Okay. So I introduced vectorization as the process of interacting with text in a form that the computer can understand, right? So we're talking about numbers here, right? In most cases, arrays. We considered, splitting the data into tokens, right? Which helps to separate, either data into words or characters or subwords, like we extensively discussed. But then, about numbers, how do we go about that, right? So the first approach is one-hot encoding, right? With one-hot encoding, what happens is you are trying to you are going to create a vector, right? So so I have an example in the text here, right? So let's say we have the text, the ultimate answer is 42, and this was the only text in our corpus, right? From the class today, you understand that if we arrange them in the order in which they are, right, then the vector corresponding to answer may have the text okay, so the vector corresponding to answer may have the array 00100 because answer is like the third word, right? But in the case where we represent the word or the vector in like an alphabetical order, right? The vector for answer will be 01000, right? Because now we're no longer representing it just in the way it appears, but like we're defining the alphabetical order and saying, okay, let's impose that on it. So we have 0100. But an interesting question I want to ask you guys is why is 1 not the first value in the vector? Because we see that answer starts with A. A is the first alphabet. So why is 1 not the first value in this vector here? And if it is not, what might be, what word essentially will have the first, we'll have 1 as the first value in the vector. So it's an interesting question to think about. What do you guys think? And if you don't get a question, what I'm saying is,
can you repeat the question, please?
Yeah. So we have the text. The ultimate answer is 42, right? It's an interesting text. When we encode answer, right, in the order in which the text appears, we have 00100, right? But when we encode it in alphabetical order, we have 0100. 0, 0, 0. The question is, in this second instance, when we encode it alphabetically, why do we have it as 0, 1, 0, 0, 0 instead of 1, 0, 0, 0, 0? Since answer starts with A, and A is, the first letter of the alphabet, and this is alphabetical order. Does anyone have any idea?
I'm just looking at the indexing. I'm just looking at it, just trying to make sense of it.
What do we think? What do we think? Okay, so we have some good answers in the chats. Olatunde, Lamilola, Kelvin, and Usman, they're all correct. Numbers come first. So if you try to sort, the words in this, let's even do that. This is all we're here to do. All right. So if we try to sort let's split. We're not going to bother about the punctuation for now, but let's just split it and sort. Sorry, it should be sorted. All listed sort. So we see that when we attempt to, okay, there's one more thing I need to do, sorry. Remember that, like I said before, when we're dealing with, free text like this, we prefer to just make everything lowercase because it makes our life easier. In that case, you notice that you put D second because, capital letters interestingly come before small letters in the character table, the ASCII table that you guys were talking about in the lecture today. So we see that, okay, it comes second, right, in lowercase. So that's why. Anyway, diving into things, what's happening here is we are trying to hot encode the data. What we first do, really. So the idea behind hot encoding is, you assign every word a position, right? How you're assigning the position, like I just showed, is a choice, right? It could be in terms of how they appear, right? Or in like an alphabetical order. It will not, either way, right? There's lots of context. So it wouldn't matter too much. While one might give you better result than the other, it won't matter significantly because, in either case, you're still losing context. So what we just do is we take out we look through every line, right? Every sentence, and we take out every token in every sentence. So this is a nested loop for sentence in the lines, and then for token in sentence, we lay every token bare. Essentially, we are flattening the list into a single list, and then we convert that to a set, convert it into a set so that we only take unique words. Remember, you guys were talking about when we were talking about the quick brown fox jumps over the lazy dog or something like that in the lecture earlier. You notice that D was represented by the same vector because you don't want to assign multiple vectors to the same word essentially, right? And then after you do that, you sort it because the set on its own is not sorted, right? So you want to sort it so that it means you are defining the order you are defining now. In this case, is what we define just up here, alphabetical, right? So you sort it. Next thing we do is we use the one-hot encoder from sklearn. So sklearn, some of you may be familiar with sklearn because you've used it briefly in some labs, if I remember correctly. But sklearn is a library that provides you with an easy to use access to models and some pre-processing functions, things like that. So also metrics. So it's useful. It's one of the libraries that you probably interact with first as you progress in the lectures and lab to come. But what happens here is we use the one-hot encoder, right, to first assign values or assign like indexes to every word in our vocabulary, right? So we can really take a look at vocabulary if you want to. All right, so if we decide to take a look at what is in vocabulary, is literally, an ordered list, right? So that's what vocabulary is. So we assign like the category to vocabulary, and then we initialize a list for the one-hot encoding, and we say for every sentence in the line, in the constitutional lines, right? Let's fit each sentence to fit and transform really each sentence using this encoder. What fit transform does, right, is it essentially takes each word, right, in the sentence, which is now, talking to 42 answer is the ultimate, right? It takes each one of them and then it finds their corresponding, position in the array that we created for all the words, and then assigns that position to a value of 1, right? The same way we're talking about this, and we said, oh, we'll assign answer to a value of 1 and every other value to values of 0, right? So it makes sense. And then we do that for every sentence in this loop. TQDM here, by the way, is just it's just for this, visualization of the progression, since it took like some seconds for it to run. So sample, when we look at the samples here, we see that for the first sample, after we encode it, right, we have an array that is 7 by 3547. And what is 3547? 3547 is the length of the vocabulary, this guy. So that's why I decided to print out the length of vocabulary. You see that we have arrays for every word, right? And then, so it means that for a full sentence, right, which is split into words, the encoding will be the number of words in the sentence by the number of sentences in our whole vocabulary, which is a lot. But that is what happens with one of the encoding, right? And we can split this out to any word you want. So you could have like 42, right? And we have 8 and 3, 3547. Yeah, so all this, we can try out all this things, because in this case now there are 8 words in the sentence. So when we encode it, we also get 8, but then the vocabulary length is constant to the same thing, right? So this is one of the early ways we went about handling encoding of words and sentences. But then another approach is using term frequency in document frequency. In this case, what's happening is we're trying to hold more information, right? Because like I said, one of the encoding is just positional in an array. But what if you want to hold more information about, at least a little bit more information about the relationship between the words in a sentence, or the sentence in the whole document, right? So this is what the TF-IDF helps us do. First, term frequency measures how frequently a term occurs in a document, right? A document in this case are sentences. So we're saying for every sentence, how frequently does the word occur in it, really? And it's pretty direct. So what we just do is we define a function to compute the term frequency. In this case now, the document is a word tokenized list. So something like this, right? And we say, okay, given a word, how many times does it occur in the document? Lists have a method called count. So we're going to do list as count word. And then, you can do length of the document, and we compare the amount of times it appears in the document to the number of words in the document. It's just a simple frequency estimation. So we do that. Let's round up again. Okay, so this is a different list now, since we've changed some things at the beginning. Remember that we changed some values at the start to experiment with. So here we have staff of house of assembly. All right. Interestingly, of appears twice also in this sentence. So when we compute the term frequency, we say that it appears twice, and then there are 5 words. So 2 over 5 is 0.4, and that's what we have. Pretty direct. But if the word does not exist in the sentence, it will be 0, right? And it's an interesting thing because it means that any word that does not exist in the sentence will have a term frequency of 0, right? So just hold that thought. Next, we do inverse document frequency. So this one measures how unique a term is across all the documents in the corpus. Meaning, what we're just trying to find out is, in how many sentences does this word appear? That's what we're trying to find out. So in how many sentences does this word appear in the whole corpus, right? Remember that the documents we're talking about are sentences. So across all documents, across all sentences in the corpus. So what we just do is we pass in all the lines and then the word, and then we try to find out how many documents rather contain that word, right? So you say that we look through the sentences, and then we say if the word is in the sentence, we return 1. So this just sums up a number of ones, right? And then it gives us the number of documents that contain that word. Then we use the formula. So the formula for the TF-IDF, like you'd have seen in the slides, in one of our last slides earlier today, was the length of the documents, right? Or the length of the corpus, the whole corpus. So every number of sentences in the corpus divided by the number of sentences that contain the word, right? So that's why it's called inverse document frequency. Because if we just said document frequency, we would have said, oh, since we know the number of documents containing the word, let's divide it by the total number of sentences to find the document frequency, sort of like we did for term frequency, right? But this is the inverse. So we take the inverse, so it's the other way. So number of documents divided by number of documents that the word exists in. We also add the value for 1 here, just so that we don't have a division by 0, because there are some words that will probably not even be in your data set. So if you're trying to do TF-IDF for a word that is in your data set, this will be divided by 0, and then you run into trouble. So you want to avoid that, right? So in some cases, some people add like a very small value, yeah, if you want, but we can just add 1 so that we never get a division by 0. Because I think, as everybody here should know, division by error, division by 0 would not work, right? If somebody want to say something? Is anyone unmuted? Okay, somebody.
Recording.
Someone please mute yourself. Okay, so we can compute TF-IDF for for different words. Let's try the of that we did before. Hold on. Okay, I've not run this out yet. So let's try the of we did before. 0.4. Okay, let's try constitution we did before. 2.9. Okay, so we now have our IDF. But what is the TF-IDF? Simply, we're just multiplying TF and IDF. Is that direct? So it means that if the TF is 0, then TF-IDF is 0, right? If the indeed the IDF is most likely not going to be 0 directly, but the idea is that if a term is not in a sentence, right, the term frequency will be 0. So it would have no representation. So it would just be 0. It doesn't contribute anything. 0 just means it's not contributing anything, essentially. And then we can do this for every word in the sentence. So we compute the TF-IDF by multiplying the TF and the IDF for every word in the sentence, and then we append all of those into a vector. All right, so we just put all of those into a list. So we have a list of, a list of lists. So here we can see the results. So when we try out an example, the index here is 42. We get that line. That's a word tokenized line. So WT, again, as we defined before, means word tokenized. And then we see the sentences, mode of exercising federal legislative power. That's fine. For those are, exercising power. And then we get the vector. So for here, we just display the vector really, right? But the vector is a list of all the independent or the individual TF-IDF values. So for instance, if I print vector, right, this is what I get. So just to note, so you notice that this is more condensed compared to our good one-hot encoding in quotes, right? Which had like, this times the one-hot encoding represented information in like this times the length of the vocabulary. You get, so instead of just having the length of the words, that one contains the whole length of the entire vocabulary, right? So we have like two ends of the spectrum, just one value for each word, right? And in that case, we have a whole array, right, for every word. In a to mention, like I've been doing and I will be doing in this notebook is helping you. We are calculating. Okay, so Olatunde had the question: are we computing the inverse frequency or the logarithm? We are calculating the inverse document frequency, right? But while the name is inverse document frequency, it does not necessarily mean that the formula is just going to be inverting document frequency. You get, so usually we realize that the numpy, the log, most of all these formulas, by the way, are derived by experimentation. So it could have started out as just inverting the document frequency, but if I decide to experiment and I realize that when I take the logarithm of the value, I get better results, then it means I will just go with that. Because when you take the inverse document frequency, right? So this is a large value. So we have NP dots, right? Let's say we're taking this example here, Apple. So if Apple appears in 50 out of 100 documents, or out of 1,000 documents rather, we have 1,000 over 50, right? Now we know 1,000 over 50 is 20, right? But the logarithm of it is 2.99, so it's a smaller value, right? And it reduces the chances of us running into very, very large numbers, because the larger a number is, the more difficult it is for us to the more difficult it is, or the more memory it consumes, really. That's the better way to put it. So the larger number is more memory, but you see that this now, it still contains the essence of the inverse document frequency, but now we've taken it to the log scale. And by the way, this is log to base E, not log to base 10. So we do that, and then we get a smaller value. So we do that really across different sort of data sets. So you could even have numeric data sets that you have to, or that you feel like, oh, maybe they're better on a log scale. Then you take the logarithm of those values, just to make sure that they are limited to a smaller range, right? It's the same idea behind, I think is normalization or so, where you try to restrict your numeric data into like a range of 0 to 1 or -1 to 1, right? So that's why we're really adding the log. But it is still the essence, it's just a different scale, but all we're still doing is inverse document frequency, right? All that's clear. So like I was saying, we bring it together, we Okay, but like in practice, we may not want to. We may not want to implement it ourselves, all of this ourselves. So there's a library called Gensim. I know Urala mentioned this briefly, but you know, we probably want to use this library when we are dealing with use cases, particularly in English, where they have well-defined models and well-defined large corpuses, right? But GenSim is really allows us to interact with language models with predefined predefined methods. So the first thing we do is we create a vocabulary. We just pass in our list of word tokenized lines, right? And then for every sentence in those lines, we convert those the documents to essentially bag of words. So this is doc to BOW, right? Bag of words format. And then from there, from the BOW format, bag of words format, we create the TF-IDF model by just passing the bag of word corpus to the TF-IDF method, right? So you know how the TF-IDF works. You know how the bag of word works, right? So you just see these as this is an abstraction over all the things we've been coding ourselves before, all right? And then you cannot get the vectors directly from the TF-IDF model by accessing the bag of word corpus. So this is it, all right? And if we were to try this out for a sample, it's something similar. It's similar to what we had before, right? But it's not the exact same thing because of implementation in libraries typically differ from our raw implementation. While it's good to know how things are done on a more fundamental, level, right? When libraries like this are implementing these models, they typically apply some level of optimization and some more interesting pathways to it. That's why you see that they start out with creating a bag of word corpus, right, which we are familiar with, right? But this is not how we went about creating our own TF-IDF model or vector. So yeah, it's interesting to see how different people implement different things, but the fundamental ideas are always the same. So if you really wanted to use TF-IDF, you may not want to implement it yourself. You could just use their implementation, right? And yes, one more thing is comparing sentences. So typically, right, we would have to look at sentences and then spot their differences. So if you had two sentences, say, okay, let's use the ones in this example. So see sentence 1 and sentence 2 highlighted here, right? Declaration of assets and liabilities, oaths of ministers, appointment of chief judge and judges of the federal high, right? These two sentences, they are obviously different. Like, okay, like what can be related between these sentences? You get, but how will the model know? Is a good question we ask ourselves, right? A way to help the model know really is through cosine similarity. We learned about dot products in the linear algebra class, I believe. So if the A dot B would not be too new to you, as long as you have two vectors, you can always get their dot product by comparing by taking each corresponding element and multiplying them, then summing the whole thing together, right? Then what you see under is just the normalization. So norm, I can't remember whether you covered it in the class on linear algebra. I think it was mentioned. So, but if you have a vector that is like 1, 2, right? The norm is simply, I'm not going to use the actual commands. I put NumPy the square root of right. So if you run this, okay, sorry, this is capital A. All these things are important when you're writing code. Okay, I meant to sum this, sorry. Let me quickly add the summation. So the formula for the norm is, we take every element in the vector, square them, sum them up, and then take the square root of everything. You get? So we do that for A and B, then multiply that as the denominator. Then we divide the dot product by that, right? So that's what happens in the background, but we're not doing it ourselves. We could, but in reality, you might just prefer to use a library. A number of libraries implement cosine similarity, but since we already installed GenSim, I just figured we would continue with it. So we pick two samples, and then we try to compare that similarity. We can pick another second sample to see. Obviously, when we pick the same sample twice, we should get 1, right? So the question is just that, or what this is just telling us is that we don't have, or it's more complicated to find out, to find other sentences that look or that are like this sentence 42. But if you check, I think, let me check the first two. It might be different now. Yeah, so the first two sentences are actually the same. Because I'm guessing one was the title and then one was, some other, heading in the data set. So it's obvious now that the data set has duplicated sentences, and this is one way to see those duplicates, right? Notice that the indexes are different. I didn't put the same index, but we are still getting the same sentences. So that's the funny thing about the data sets, and who knows, maybe later on you guys will explore how to handle that. Okay, so a question is now that we've created vectors, they hold some context, but is that sufficient? Why? Right? The answer is no. And really, it's just that these TF-IDF vectors, while they hold some information about frequency of a word in a sentence, or the sentence, or the words in the whole document, it does not communicate anything about the words themselves relating to each other. Right? You can compare sentences, fine, but it's not, there's no contextual information yet. So this is why we have to consider word embeddings, right? And later on, we'll also consider sentence embeddings briefly. So, but before we move on, any questions on vectorization in its entirety, any part of it, from monotype coding, bag of words to TF-IDF, and then using GenSim? Any questions at all? What was the technique used to vectorize the sentences prepared? Well, the technique is GenSim, it's TF-IDF. TF-IDF. So you notice that when we're comparing them, where is it? We're using the TF-IDF vectors that we defined just here, right, under the GenSim TF-IDF. Now, another thing to note is it is easy to use GenSim TF-IDF because the vectors or this util that has been created by TF-IDF, right, works for comparing even the vectors that may not have necessarily the same the same shape. So let's try to even, let's see. I want to check. Let's confirm the shape of the first two, by the way, will obviously be the same. It's because they were the same words, if you remember. Right. But when we had different values, 073, right, then we get different results. So we're using GenSim, right, mostly because of the vectors in this case are easier to compare using cosine similarity, since there is more, since their units or their dimensions are more, they're correlated, as opposed to before when we're having, you know, different sizes for vectors depending on the number of words in the sentence, right? So that's really the idea. That's the idea. So on your notebook, you can experiment with other ones. You can see why you may not want to do this directly with the other, with the vectors we implemented ourselves, without doing some estimations to make sure that, or to some approximations really, to make sure that the dimensions are the same. So let's go. I want us to take a quick look at the samples before we continue into word embeddings. By the way, it seems that we're going to run over time. So like you did, what was it, last week? So if you are open to me taking some more time, just let me know. Else, you know, I made the notebook quite explanatory, so I'm sure you still get most of the context. And then you can always ask questions on me. Okay, hold on, sir. I want to do NumPy the shape, since it's a list. But both of them, just to see their shape. So one of the benefits of using the GenSim is that while these vectors don't have the same shape, right? This function was built to compare GenSim vectors. So we're not running into the kind of trouble we'll face if we're using, right? If we're using this function on our own vectors, which we created ourselves. So it's interesting to note. And these vectors are not, you know, our vectors were, if you remember, our vectors were like single lists, right? So let me just scroll up, see a single list, right? So no second dimension. Vectors here have a different shape, right? So you would not be able to use this exact function to compare our own vectors, the ones we created ourselves. But you'll probably be able to experiment with using another cosine similarity method, right? Or from a different library like SciPy, for instance. So there's that. So yeah, we're working with GenSim TF-IDF. Now on word embeddings, by the way, please in the chat, I want to see if, you know, you guys are willing to give some more time so we can conclude, or whether you're prepared to go through the notebook. We are nearing the end really, but it depends. Also, by the way, Charles, did you get what I just described? As regards the technique we used. Okay, thank you, Charles. Thank you. Okay, so what embeddings, right? We've learned, you know, quite a bit about what embeddings in class today, but the question is, the fundamental question that what embeddings are trying to understand is, or trying to answer is, how can we get even more context from the words, right? Context about their relationship with each other, all right? How can we get this kind of context from the words? To do this, you know, word embeddings are one of the most direct ways, right? Typically, when you're working with English, it's advisable to use already trained embeddings so that you don't have to bother with gathering too much data to cover the entire English language. But if you were dealing with another language, maybe Yoruba, right? Or you're dealing with like some scientific languages or a very specialized corpus that is not like a general, that had like specific, context and words, then it might be better for you to create your own embedding in that case, right? But for most English applications, you probably want to use a pre-trained word embedding, and that's what you would do in practice, even when you are working with tasks that have to do with embeddings. So what I'm downloading right now is an already prepared Google embedding. I set it up so you don't have to download it yourself. So once you run this cell, it just downloads to your folder by the side here. Find it downloaded, and it's pretty fast, though the file is large. So you can just quickly do that, and then we can run this. So this unzips it because it's a compressed file. So while that is running, we're still using Gensim, by the way. So we're trying to load in this already trained vectors by Google. So Google trained these vectors on about 100 billion words, right? So you can already imagine that it's unlikely that you're able to, on your own, you're able to figure out you're able to gather enough data to match that first and to maybe beat that in a general context, right? Because I mean, Google just has more information than you. That's just it. So they train it on a portion of Google News, and they got these vectors, and they shared it publicly, so it's available for use. I downloaded this, by the way. Here I'm just downloading this from Google Drive. So the link to the drive shows when you start downloading, in case you want to check it out from there. So let's load all this. So we load the word vector. The word vectors really is a dictionary, right? It's a dictionary of you can print the, let's try this. I'm sure I'm not the dictionaries from either before either before. Okay, yes. This is the method I want to call. But from my dictionary before from Python knowledge, and maybe the first class we had and the Python refresher. So we see what we have here is simply a dictionary, right? With the different words, like, and then they have different indexes, right? So we have the number of dictionaries that make up the whole word vectors. So key to index, there's another index to key, right? But all of these are what we use to implement or to interact with the embeddings via Gensim. So this function simply just loops through every word, checks if they're in the word vectors. Hopefully they are there, right? And if they are there, it gets their embeddings. To get the embeddings, we just ask for the embedding of the particular word, like you do from a dictionary, right? So we use a square brace, and then we collate all of that. So when we do that for this, we get 5 by 300. So different embeddings train the different models really have embeddings with different sizes. This one has 300, right? So embeddings have like 512, right? But this is definitely better than the case we had before, where we were having something by over 30,000 plus. So while this is more than a 5 by 1, it's still less than a 5 by 30,000 or something, and it holds more information contextually. So a way to understand why or how we hold more information is by comparing. So this is, they compare on a scale of 0 to 1, right? So we're just checking for if the first word is in the vectors and the second word is in the vectors, then let's find the similarity between the two of them using the dot similarity method from the word vectors. all right? So we do love, hate, right? Love, hates, I mean, they are related, right? While they might be opposites, but the fact that they are opposites means they are related. So that's why you see that we have a value of 0.6, which is significantly high when you think about the fact that the scale is 0 to 1. Then also compare constitution and law. It's interesting to see that it's also correlated, but all that I expected is to be higher. But 0.54 is still not a bad correlation between the constitution and law, since probably law will probably be represented in different contexts. Also, school and students have something similar, right? 0 and 0.6. Atoms and electrons, for those of us that are more sciencey, right, have an even higher correlation because atoms and electrons. But yeah, we can also visualize embeddings. So I selected some embeddings. This is one of the more interesting ways to visualize your text. So what we have really is an 11 by 300 embeddings, right? Because there are 11 words here. We're trying to see which of these words will be closer on a plot, right? When we plot the embeddings. But this 300 means that, the dimension is quite large, right? Because, to plot this in 2D, we need 11 by 2. But currently we have 11 by 300. So what we do is we use this method from scaling. I know some of us are familiar with PCA. I think it was also mentioned briefly in one of the previous classes. That's principal component analysis. All right. This method uses PCA under the hood. So just look at it as it's doing something similar to what PCA does. But now we're trying to get out just 2 components from this 300 we had before, which means a lot of information, obviously, but usually it still contains some relevant information, which is why the plot works. So we transform the word embeddings that we have here, that we pass into the method, and then we loop through and we plot using plt.scatter, and we label it using plt.text. So when we define this function, we're defining a function now because we'll use it with other embeddings. So as we see here, constitution and law are quite close to each other, meaning they are related, right? And then we have word and language. We see that they are also quite close together. Something that's interesting is, though we have book and paper close to each other, we have computer relatively close to them, which is an interesting relationship, if you ask me. And then we have natural and artificial. We have hate and love. So it's sort of like they're just in buckets like that all around. All right. We could plot a lot more words than this, but it can quickly get messy. All right. But you can experiment with that. So I encourage you to add some more words to this list, or even just get out the vocabulary. We already have a defined vocabulary for our, I believe, for the constitution data. So you can try it out and see how it models things up, and then maybe limit it to like 50 words and see what you get on this plot. But yeah, before we move on to the next word embedding, you can also compare sentences. We've been comparing words, right? But what if we wanted to compare a sentence? To do this, we call back the word tokenize method from NLTK that we used earlier at the beginning. And then we just really compare. We're comparing the list of tokens. That's what we're doing. All right. Now, because of these 2 things are right, so right to freedom of expression and the press, right to freedom from discrimination, which are from the Constitution, we see a relatively high similarity, don't you think? And I mean, they have similar words in them, so it's not far-fetched. And then when we run this also, we see also what I would call a reasonably high similarity. I won't say why, because like 0.5 for this sentence and a sentence that's all this sentence has really is right, but it's not particularly saying the same thing or in the same exact context as this other one. So 0.5 might be high, but you know, different tokenizations, different embeddings, you know, have different understanding of different words. So it just reflects how important it is that you know the context you're dealing with, and you make sure that you are using techniques that work for you. So it means that if I was to define, if I was really to define whether two sentences are similar using this GenSim, right? I might not want to have a threshold that is, you know, 0.5. I might want to have like a 0.6, 0.65, maybe even 0.7, right? Because these two sentences are not really alike, are giving a relatively high similarity score, right? So again, any questions before I move on to spacing? What we're going to be doing next is similar to what we just did. So we'll just quickly run through it for spacing and then training and word embedding model. But any questions for as regards getting similarity, working with GenSim, visualizing the word embeddings? Any questions? But we were over time again. I didn't get any notice in the chat about whether we are comfortable with staying over or not. Should I assume that we are good and we should just continue? I need you guys to speak to me. Okay. So let's do that. Okay, so with Spacey was also mentioned by Worola earlier today, briefly. So you may not have heard it, but it's another library that you can use to interact with embeddings. So in this case, we download an already created embedding by Spacey. It's their large, LG is large, so it's their large English embedding, and we load it into our environment. So first we explore using it to tokenize the sentence, and we see that, you know, it's able to tell us that, okay, this is a pronoun, sentence is the noun here, the full stop with the punctuation is, you know, auxiliary, things like that. So it knows what the parts of speech are, which is useful because, you know, like you learned in the lecture, you can use this to extract information about part of speech if that's relevant to you. Right? The model here is already trained to do this. That's why you can do this. All right. Also, a brief segue. We didn't do this with GenSim, but it's interesting to also know that you can lematize. So we're allowed to talk about lemmatization in class briefly too. But what happens here is we're just converting a word to its base form, right? So she remains she, but we convert was to be, right? Convert fighting to fight, convert children to child. So that words like children, child, that have the same base word, like in the same way. That's the idea behind lemmatization. But also it removes context, because she was fighting for her children. It's different from she be fights for her child. Like, you would agree with me that they're different when you hear them. So this one almost sounds like pigeon. So it's interesting to note that, you know, while lemmatization is useful, you also want to know the context you're working in. So you don't just use it, you know, arbitrarily. Okay. So before I continue, who is with me? I need to know those that are also running this on their end and at this point, because we'll have a short quiz soon. So it's important that you also follow in on your end. You cannot drop a message in the chat so I know that we are together. Anybody with anyway, that with me running the cells on their end and also seeing the results or similar results to what I'm getting. Okay. Nice to hear. So yeah, we do. I don't take too much time over, but let's see how much we can cover. So we're doing similarities, similar to what we did before, but the function is slightly different. So here we create the first word vector, and then we compare it using the dot similarity method in spacey to the other words, right? We do the same for constitution and law. We also try it out for Afrobeat and music, right? We also see we have relatively similar, values, right? Still around 0.5, 0.6. And also we can visualize the embeddings in the same way, really. The only different part is getting the vector. In this case, we're using the dot vector method in spacing. And we have similar results. So love and hate, artificial, natural, constitution, law. I think word and language are slightly more spaced apart here. You have book and paper, right? When you run this on your end, you might not get the exact same thing here because it does not when the dimensions are being reduced, it doesn't happen in the exact same way every time. But you always realize that things that are close will still be close. It just might be, up, you get, or like arranged differently. These are some more words that are more that you can find in the constitution data data sets that we have. So we can also see writing and language, word, Yoruba and Nigeria, customs, law and constitution, approve, objection. We're trying to see how these words are related according to the word embeddings. And finally, on word embeddings, we can also experiment with creating our own word embedding model, right? It's pretty direct. What we just do, we just pass. So we take the word to vec model, and then we pass our sentences in. These are word tokenized sentences, right? We declare the size of the vector we want. Before we can leave it as 300 too. We had 300, so we can leave it at 300, and then we declare some other parameters, and then we run this. It's pretty fast. So when we do the model back, we can compare words again. Now, in this case, when we train the model on our data sets, we're getting a higher similarity between constitution and law. And it's simply because now the data set is more focused. So there are probably more relationship between constitution and law in the constitution as opposed to like just a general body of text that was used to train all these other models. So that's why you see higher results here. But also this model does not know every word. So if we try to use the model to check out students and school, we don't get any results. We get an error, right? Because our student is not present. While school is present, student is not present. So that's a troubling limitation. It means you just don't have enough information when you use your own model like this. So you have to be sure that the context you are using it in is limited to what you are dealing with. Okay, and also we can visualize the embeddings as we did before. As you see here, law and the constitution are almost overlapped, right? And then we have Nigeria somewhere up here. Language and Yoruba are close, I guess. Also customs in this case. So you see that this is not this is probably not, while some of them seem reasonable. you wouldn't say you're getting the best of of the embeddings from just this. So it's important to note that sometimes it's better to use pre-trained models. Okay, so we are close to the end, but I want us to do a quick quiz, right? And I want to share the link, so hold on for a bit. After this quiz, I'll just do a brief walkthrough before we wrap things up. So I'm going to send we're going to use Slido though, so you can check the what's the name? You can open the website first, and then I'm going to send the code now to you. So expect the code in the chat soon. Hold on. Okay, so just go to Slido 2. And I want to see if you guys are here, so I can see from here. So if you just type sli.do, it should redirect you to this place. So once I see you guys here, I would start. Let me stop sharing for a while. So I see Charles here. I see Chinelo. When I have, say, 10 people, I'll start the quiz. Let's try to join quickly. Is anyone else joining us? Okay, so I'll let somebody here. Oh, it's taking time to log in. Let's see. Some people can get in the next 2 minutes, so we don't take too much time. I don't want to go too much over time, so maybe after this quiz, we'll just do a brief discussion before we wrap things up. Okay. So I have 6 people. Let's start. I guess anyone that joins after will just probably miss the start of the quiz. So can you guys see the first question? Okay. I think most of us got this question right. Hooray. Okay, I think most of us are getting the second question right. Looks good. I guess some of it is a bit tricky. But yeah, let's pay attention to the word.
Hello, please. The timer is too fast. We can't even read before it will get off.
Yes, we're testing your speed and accuracy. Okay. Yeah. Okay. This one, I'm not expecting anybody to miss this one. Should not be getting this. Guys, TF is term frequency. Term frequency. Okay. Okay, this one is important because I'm going to talk a bit. So if you just use a threshold of 0.5, right, it means that you are just assuming that regardless of the embedding, right, regardless of the way the embedding is trained and all of that, once the threshold is greater than 0.5, you are good, right? And it's not always the case. So what you want to do in practice is you want to study the embedding a little bit. You want to study the way it, the way it assigns similarities to sentences, right? So you compare a lot of samples, do some investigation first before you now decide that, okay, this should be a threshold. And generally that applies to any area of machine learning that you need to use thresholds in, right? you probably want to investigate it a little bit and see whatever is generating that threshold, what's like, how is it generating those thresholds, right? What's the range of values, and based on your interpretation, what should be the threshold. In some cases, 0.5 works, but not in all cases, so you want to be careful about it. Hooray. I have 100% on this one. Read quickly, read quickly, read quickly. In this case, I don't know why we all missed that, but let me quickly go back. In this case, right, if you checked out if you're paying attention to the word embeddings we dealt with, we had some that were like dimension was 300, most of them were 300 that we've done so far. I also said some of them are 512, but they're typically not too large, right? In some cases, they could be in the 1,000, maybe when you're dealing with like a sentence level embedding, right? Which we'll talk about shortly, but on the word level is usually tricky. So you don't want to. Though only one person answered this, but still. Also, word to vec and glove are actually word embeddings. So yeah. Okay. So in this case, again, pretend embeddings like like you said, are usually trained on a lot of data, meaning they are always larger than what you have with your own smaller data, unless your data, is that large, in which case, you're an interesting person, right? And also, they're not always easily available depending on the kind of data you're dealing with. So you might be dealing with like some other language, some either African language or any language that is not just publicly available. Yeah, is the popular languages like English, French, all those colonial masters languages that are typically more studied outside there, and then they have embeddings publicly. But it might be difficult for you to get embeddings for for some more low resource languages. So it's important that that it's not always available, right? Um, but a reason why you would probably not want to train your own embeddings is when you assume that your own embeddings are always more accurate. I think the keyword is always, because in some cases it might be more accurate. But since it says always, you probably don't want to pick that option. So this one, what do you guys think? Do you prefer word embeddings to sentence embeddings? Some say true, some say false. Interesting. So yes, false. So reason why simply is because word embeddings, like we said, they hold relationship between words, right? But not necessarily, relationship across sentences. While you can aggregate the word embeddings for a particular sentence, so for every word in a sentence, you put the word embedded into an array and then you aggregate it. While that works, really, right? You may not want to, or you may not just be able uh, to use that on a sentence level, right? So if you can get a sentence level embedding, they are definitely being put in a better situation, and and then you can use that to do some more analysis. So we typically prepare sentence level embedding to word embeddings, unless the kind of task you're working with is on a word level, and nowadays that's not usually a popular thing to say. So yes, prefer sentence embeddings, please. Okay. So I have an interesting turn of events. Charles had the highest points. Through to Charles. I think I've been seeing him in the chat. So it's good to note. If you had any questions about any of the questions that we just covered, please let me know. Any questions about the questions? Aside the time, because I know someone already complained that the time was not enough. Any questions about the questions? Uche, I can quite relate to your situation. So what we'll do right now is, I know we are yet to even pick a time to have Kenichi's follow-up class on linear algebra, right? Which I'm reluctant to, also put up a goal for that. But really, what we have, yeah.
Do we have much to cover left? I don't think we need to reschedule, unless we have so much to cover.
No, it's not significantly much. We can definitely cover it. I just really run through it since the notebook is explanatory also.
Okay. I think we just encourage folks to go through it, and if there is any question, they can put it on Discord and ask. And you can schedule a meeting with people if they would like to chat with you about that, but not to overload ourselves with classes in terms of the classes we did not finish, because there's already Kenichi promised a class, which we have not also done yet.
Okay, that's fair. So I believe the last 3 sections are on sentence embeddings, which really you're just going to be exploring using Spacey and the Google sentence encoder, as well as Cohort, the Cohort sentence embedding. So it's pretty direct. As long as you understand the word embeddings that we just did, that one is even more direct than this. So you just need to just run the cells and see how it works. But it's pretty much the same, particularly for the spacing. So just take a look at it. And then we also have the n-gram model, which is also relatively direct. We don't delve into too much of the detail, but I've made the notebook well explanatory. So like I just said, if you have any questions about the n-gram and embeddings and the last bit on evaluating language models, which is also pretty short, then you can, drop a message on Slack, also on Discord. I don't know why Slack is menu. And I'll definitely respond to that. Always monitoring the channels there. So just let me know if you have any questions right now, and then also later on when you go through the last 3 sections in the notebook. Because it's important that you have an idea about all these things. But there are mostly things that the entire notebook really can be run once if you just run everything runs and you're good to go. So you can just walk through, the code in those cells. If there's anything that is not too clear on first glance and second glance too, when you do some Googling, right? Then you can just drop a message on Discord and maybe others will learn from it too. Okay, so So for Cohort, you just need to go to the Cohort website. I don't know if you're familiar with all this API business, but once you, so if you notice the Cohort subsection is like is a hyperlink, it's in blue. So if you want to just click that link, create an account, and just get your API key. Your API key is given to you for free, so it's not something you're paying for, but it's an interesting API to try out because they also have a multilingual API, that works across multiple languages, including Yoruba. I think I also saw Igbo and Hausa there. So it's an interesting API to try out. I'm going to paste the link, though you can just click it on the notebook, but the link is in the chat. Just you see the creating you see the account option, I think, in the top right. So just navigate there, click it, and then create an account. Maybe it's your Google account, and you see on your dashboard, on your Cohort dashboard, you can just access your API keys. You don't need to create one. There's already one created, so you just copy it and paste it into that cell, and then you can run every other thing. So yeah, it should be fun. Let me know what you guys think about the rest of the notebook. And I'll probably send the assignment also. It's already.
Oh, Angie, if you have any question about the Cohere API, you can put it on Discord and tag at Cohere, because we ran an hackathon together a couple of months ago, and a lot of Cohere folks are still on the Discord channel, and the role is at Cohere. So Roy is probably also still on the channel, but you can also go to the Cohere Discord channel as well. Also on that channel, if you have any question about that. And if you study our YouTube link, if you go to our YouTube channel, you would see that we have a playlist on the Cohere AI hack that was run just before this cohort started. And there we also had some workshop where Louis from Cohere, who is the lead for the developer relation, you probably know him, is very well known in this field. Also, I gave a talk, and a couple of other people like Sarah and the likes. So if you want to watch those videos as well, you feel free to have a look. But in general, once you start playing with Cohere and you have some question or something like that, do let me know, or just put it on Discord and I can ping. We'll maybe able to help out if we can.
All right, thank you, Kevin. So I think that will be it for today. In general, I think what I really want you guys to take away from this session, I think from this week really, is that as you learn about different algorithms, going into the next couple of weeks, and eventually at the end of the course, you need to also it should be easier for you to think about building projects that involve pretext, whether it's classification or some generation, right? It should just now be more at the back of your mind. You should not be thinking just about tabular data or things like that, because I know those are the things that we might be more familiar with. But now, with an understanding of how to process text into numbers, right, it should be easier for us to think about how to build models to solve language-related tasks. So I hope you guys enjoyed the session. I encourage you to go over the entire notebook. If anything is unclear, just drop a message on the Cohort 8 channel so I can answer, and then others can also learn from it. And yeah, thanks for staying till this long.
Okay, thank you everyone, and have a good rest of your Saturday. Thank you so much, Fortune. Bye.
Bye.